Hello everybody and welcome to my presentation. Thank you very much for tuning in wherever you are in the world. My name is Callum Littlejohns from the University of Southampton, and the subject of my presentation today is programmable circuits using silicon photonics technology. Now, I'm aware that many of you listening may have an electronics background, so this slide is intended to introduce photonics using the example of an optical communication system, and it shows the evolution of optics over the past 30 years from back in the 90s, where we had long haul communication systems that were optical, and moving to the modern day where the optical systems have penetrated into the data centers to even shorter propagation lengths, where current technology is really pluggable optics into the back of your switch. Now, the next iteration that is presently emerging is the full integration of electronics and photonics co-packaged onto the board itself. So why are we doing this? Now, I've highlighted on this slide 3 key reasons. The first of which is that with photonics we can achieve a greater bandwidth density because we're able to exploit wavelength division multiplexing, whereby we can send many different signals on the same channel. Secondly, we can achieve a more energy efficient interconnect. And finally, and perhaps the most crucially, we can achieve a lower cost per gigabit per second. And on this final point, this is where silicon photonics really comes to the fore, particularly when we're talking about on-chip interconnects and devices that are co-packaged alongside electronics. So what is silicon photonics? Now, as this slide says, it is the implementation of high-density photonic integrated circuits by means of a CMOS process. Now, this means that we're able to exploit all of the know-how and all of the infrastructure that's been built up by the electronics industry over the past several decades. And this leads to the ability to design and fabricate complex photonic chips at a very low cost that achieve some of the key benefits that I highlighted earlier, such as a very high bandwidth density. So how do you get access to a silicon photonics line? Now, over the past 10 years or so, many silicon photonics foundries have emerged, and in fact, based in Southampton in the UK, we have formed a silicon photonics foundry known as Cornerstone. So Cornerstone is unique in that it's the only silicon photonics foundry service in the world which, in the spirit of the OCP, is truly open access. Now, what I mean by this is that at Cornerstone we offer access to a silicon photonics process via a multi-project wafer service, whereby all of our processes, our standard components, our process design kit, they're all open access and available to download from our website. And another way in which we differentiate ourselves from the other silicon photonics foundries is that we like to give the researchers some flexibility to enable them to innovate more readily. And by this we mean that we're open to customizing the process flow to enable new and novel devices to be developed. And finally, a crucial point about Cornerstone is that our technology is centered around a deep UV projection lithography tool. So this means that all of the technology that's developed through us is scalable insofar that we use the same process technology as the other foundries which can offer higher volume manufacturing. So this is some typical devices that we're able to fabricate using Cornerstone. ranging from passive devices, being simple waveguide structures, up to complex active devices such as modulators based on carrier effects. And using this technology, we have demonstrated modulation up to 56 gigabit per second. Now at present, all of the Cornerstone processes are based on a silicon on insulator platform, which is really the mainstream platform for silicon photonics for applications mostly targeted around data centers. But we're very pleased to tell you that we have now secured additional funding to enable us to introduce many exciting new platforms, which will result in the ability to extend the wavelengths that are supported all the way from the visible wavelengths up to the mid-infrared wavelengths, that will allow researchers to exploit applications such as LiDAR, such as sensing in the mid-infrared. And all of these platforms will be available in Cornerstone in approximately 2021. So moving on to the highlight of this presentation. Now I've introduced several of the key advantages and selling points of silicon photonics, in that we can exploit existing infrastructure and we can enable very high-speed devices at a very low cost. But one of the leading issues with silicon photonics, particularly resonant devices like the ring resonator shown in the top right of this slide, is that they are phase sensitive, which in turn means that they are extremely sensitive to fabrication tolerances. Now, even though state-of-the-art fabrication techniques in silicon are extremely good and well controlled, even a 1 nanometer error in the dimensions of the waveguides will lead to an error in the resonant frequency of a device such as a ring resonator. Now, this is a problem if we need to operate at a very specific wavelength. So what is typically done is that over the ring resonator we introduce a heater, a localized heater, so this can tune the device to the exact wavelength that we want using the high thermal optic coefficient of silicon. And you can see in this way that if we have 1,000 different devices, because of the fabrication error, they might all work at a slightly different wavelength, but the heater can tune them all back to the desired wavelength. Now, the problem with this technique is that these heaters are permanently on and permanently consuming power. So you can see how this isn't really ideal in terms of energy efficiency. So we have developed a technique where instead of changing the refractive index and therefore the phase using the thermal optic effect, we introduce an implantation step where we actually damage the silicon crystal and amorphize it and change the refractive index in this way. Now we do this by implanting germanium through a mask into a small section of the ring resonator. So if we now turn our attention to the graph in the bottom right corner, the dotted line will show the typical resonant response of a ring resonator with no implantation. And after we've implanted a small region, we've changed the refractive index in this area, and therefore we change the resonant frequency or wavelength to the value shown by the blue curve. Now obviously this is a fixed shift and it's a function of the mask that we choose to implant through, but this can be done on a wafer scale. So the next step, and this is the nice part, is that we can then go and measure this device live, figure out what the resonant wavelength is, and then using a laser annealing process we can locally heat the device using this laser, which will then recrystallize the silicon and re-establish its initial refractive index. And in this way we can tune the device back to where we started or to any point in between. And crucially, this can be done live and locally. So we can sequentially measure every ring resonator in our circuit and tune it back exactly to the wavelength that we want. And the crucial thing to note here is that this is a permanent shift. So once we've done this, we don't need to consume any more power to correct the fabrication errors. Now we can take this concept further, and rather than just trimming out fabrication errors, we can now use this technology to create programmable optical circuits. So what we've done here is we've replaced the ring resonator device with a Mach-Zehnder interferometer device, but we've used the same concept of implanting a selected region of the device to change its refractive index. And as you can see from the graph in the bottom right of the screen, initially, before we do any annealing, all of the light is coming out of the drop port. And then what we do is, now in this case using a localized heater instead of a laser annealing process, we can heat the silicon and therefore recrystallize and reform the original refractive index of the silicon. And as you can see by the graph, in this way we can switch the light from the drop port to the through port. So you can see how this is now a programmable system, in that after fabrication we can tune it to send the light through one port or the other. Now in the previous example I said how we recrystallize using a laser, but we've developed this even further to enable us to use a localized heater to do this recrystallization step. And this is advantageous because it means that even after the device is packaged, we're now able to change its configuration simply by flowing a current through this heater. So now you can see how, cascading many of these together, we can create a programmable circuit, and we can selectively tune where we propagate the light. That brings me to the end of my presentation, and I'd just like to conclude by highlighting some of the key benefits to Cornerstone as a silicon photonics rapid prototyping foundry service. So Cornerstone offers a scalable process technology with unparalleled process and design flexibility in a plethora of open access platforms. So thank you very much everybody for listening. If you're interested to find out more about Cornerstone, you can scan the QR code in the top right of your screen and it will take you to our website. I'm now happy to take any questions.